Humanity has always gazed at the stars, dreaming of reaching them. Our fascination with the cosmos is woven into our culture, inspiring stories of faster-than-light travel from Star Trek to Star Wars. FTL travel is more than fiction. It symbolizes our desire to overcome boundaries and explore the unknown. The vastness of space makes FTL a necessity for interstellar exploration. Without it, the stars remain out of reach. The quest for FTL challenges us to push the limits of science and imagine a future beyond our current reality. This journey explores our pursuit of that dream. The speed of light is the universe's ultimate speed limit, set by Einstein's theory of relativity. Even at light speed, reaching the nearest star would take years. Crossing the galaxy would take millennia. For humanity to become interstellar, FTL travel is essential. The laws of physics present immense challenges: infinite energy requirements, time behaving strangely, and threats to causality. Yet scientists continue to search for loopholes. Could we warp space-time or find shortcuts through hidden dimensions? These questions drive the frontiers of physics, blending imagination with scientific inquiry. The pursuit of FTL pushes us to rethink the very nature of reality. To understand FTL, we must first grasp why the speed of light is nature's ultimate limit. Einstein's relativity shows that as we approach light speed, energy demands become infinite and paradoxes threaten causality. Despite these barriers, human imagination persists. Theoretical ideas like the Alcubierre warp drive and wormholes offer hope, suggesting ways to bypass the speed limit without breaking physics. These concepts push us into realms of exotic matter and new physics. The quest for FTL is more than science. It's a testament to our drive to achieve the impossible. It's a story of challenging the cosmos, inspired by hope and curiosity. The speed of light, CE, is a cosmic constant, about 299,792 kilometers per second. Unlike other speeds, it's the same for all observers, no matter their motion. This constancy shattered classical physics and led Einstein to redefine space and time as flexible, not absolute. The speed of light isn't just a technological barrier, it's a law woven into the fabric of the universe. To exceed it would mean breaking the geometry of space-time itself. This is why CE stands as nature's ultimate speed limit, shaping the boundaries of our exploration. FTL travel would require rewriting the very rules of reality. Einstein's relativity unified space and time into space-time, revealing that motion affects both. Time dilation means that as you approach light speed, time slows for you compared to those at rest. The famous twin paradox illustrates this. A space traveler ages less than their earthbound sibling. Length contraction means distances shrink for fast-moving travelers, making journeys seem shorter. These effects are real and experimentally confirmed. However, while time dilation allows individuals to reach distant stars within a lifetime, centuries pass for those left behind. Relativity offers no easy solution for interstellar society. CE remains a practical barrier. The dream of FTL travel persists, challenging us to imagine new possibilities. The most direct and frankly formidable barrier to reaching the speed of light is rooted in the relationship between mass, energy, and velocity, famously encapsulated in Einstein's equation E equals mc squared. While this equation is widely known for describing the immense energy stored within mass, a more complete version from special relativity reveals how an object's energy and mass change with speed. As an object with mass accelerates and gets closer and closer to the speed of light, its relativistic mass increases. This means the object effectively gets heavier from the perspective of a stationary observer, making it, progressively harder to accelerate further. It's a cosmic law of diminishing returns. This increase in relativistic mass means that the energy required to push the object faster grows exponentially. To accelerate a spacecraft from 99% of the speed of light to 99.9% requires significantly more energy than it took to get from a standstill to 99%. As the object's velocity approaches the speed of light, its relativistic mass approaches infinity. Consequently, the energy required to push it that final tiny fraction faster also approaches an infinite amount. Since there is no infinite source of energy in the universe, it is physically impossible to provide the push needed to get any object with mass to actually reach the speed of light, let alone surpass it. This is the ultimate wall that physics places in front of us. It's not an engineering problem that can be solved with better fuel or a more efficient engine design. It's a fundamental property of the universe. Only particles that are inherently massless, such as photons, are permitted to travel at the speed of light. They are born at that speed and will always travel at that speed in a vacuum, never slowing down or speeding up. For anything with even the tiniest amount of mass, be it a single electron, a spaceship, or a planet, the speed of light is an asymptotic limit, a finish line that can be approached but never ever crossed. Therefore, the cosmic speed limit, see, is not an arbitrary rule, but a direct consequence of the nature of mass and energy. The very presence of mass anchors an object to the subluminal world, tethering it to speeds forever below that of light. Any attempt to build a conventional rocket that could break this barrier is doomed to fail from the outset, as it would be fighting against the fundamental structure of space-time. The quest for faster-than-light travel cannot be won by brute force. It requires a complete paradigm shift, a way to circumvent this law, rather than trying to break it head-on, leading scientists to explore the more radical ideas of warping space-time itself. One of the most profound and honestly mind-bending consequences of Einstein's theory of relativity is the concept of time dilation. In our everyday lives, we experience time as a constant universal river flowing at the same rate for everyone, everywhere. We imagine a master clock for the universe, ticking away these seconds, minutes, and hours with absolute regularity. However, relativity tells us that this perception is an illusion, a simplification that only holds true at the slow speeds of our daily existence. In reality, time is not rigid or absolute. It is flexible or elastic. The rate at which time passes for an object or an observer is directly dependent on how fast they are moving through space. The faster you travel, the slower your time flows relative to a stationary observer. This is not a philosophical idea or a metaphorical statement. It is a physical reality. Imagine you have a perfect, incredibly precise clock. If you keep one clock on Earth and send an identical one on a spaceship traveling at a significant fraction of the speed of light, an observer on Earth would see the spaceship's clock ticking more slowly than their own. This isn't because the clock is malfunctioning. It's because time itself is passing at a different rate in the spaceship's frame of reference. This effect is negligible at the speeds we are used to, such as in a car or an aeroplane, which is why we never notice it. But as you approach the speed of light, the effect becomes dramatic and undeniable. The classic thought experiment used to explain this involves a light clock. Imagine a pulse of light bouncing between two mirrors. For an observer traveling with the clock, the light simply moves up and down, but for a stationary observer watching the clock fly past, the light has to travel a longer diagonal path as the mirrors move forward. Since the speed of light must be constant for both observers, the only way to reconcile this is if time itself slows down for the moving clock. The tick of the moving clock must take longer to complete. This simple principle reveals the deep connection between the constancy of light speed and the malleability of time. This strange elasticity of time has been proven to be real through numerous experiments. One of the most compelling examples comes from nature itself. Subatomic particles called muons are created in the Earth's upper atmosphere by cosmic rays. These particles have an incredibly short lifespan and should decay long before they can reach the ground. Yet, scientists detect them at the surface in large numbers. The reason is that they travel at very close to the speed of light. From our perspective on Earth, their internal clocks are running so slowly that their lifespan is extended, allowing them to complete the journey. Time dilation is not science fiction. It is a fundamental aspect of our universe. Just as time is not absolute, neither is space. Special relativity reveals another equally strange and counterintuitive phenomenon known as length contraction. This principle states that the length of an object, as measured by an observer who is moving relative to it, will be shorter than its length, as measured by an observer who is at rest with the object. This shortening only occurs along the direction of motion. The object's height and width remain unchanged. So, a fast-moving spaceship would appear squashed or compressed to a stationary observer, looking shorter from nose to tail than it would if it was sitting on a launch pad. This is another necessary consequence of the universe conspiring to keep the speed of light constant for everyone. Let's return to our spaceship traveling to a distant star. For an observer on Earth, the distance to that star is a fixed value, say 10 light-years. But for the astronaut inside the spaceship, traveling at 99% of the speed of light, that same distance would appear to be much shorter. The very space between the spaceship and its destination contracts from the astronaut's point of view. This is not an optical illusion. For the traveler, the journey is not just experienced in less time due to time dilation. The physical distance they must traverse has also genuinely decreased. It is as if the universe itself makes the journey shorter for the person undertaking it at high speed. The amount of contraction is directly tied to the object's velocity. The closer an object gets to the speed of light, the more pronounced the contraction becomes. If it were possible for a spaceship to reach the speed of light, the distance to its destination would contract to zero from its perspective. This helps explain why massless photons, which travel at the speed of light, experience no time and no distance. For a photon, its entire journey across the universe from its creation to its absorption happens instantaneously across a distance of zero. This highlights the bizarre and alien reality that exists at the universe's ultimate speed limit, a reality where our familiar concepts of space and time completely break down. Length contraction is a crucial part of the relativistic puzzle. It works in perfect harmony with time dilation. Let's look again at the muons from the previous section. From our perspective on Earth, their journey is possible because time dilation extends their lifespan. But from the muon's own frame of reference, its lifespan is normal and very short. So, how does it reach the ground? The answer is length contraction. From the muon's perspective, the Earth's atmosphere is rushing towards it at near-light speed, and so the distance from the upper atmosphere to the ground is dramatically contracted. The journey becomes short enough to be completed within its brief lifespan. Both perspectives give the same result, showing how beautifully consistent relativity is. It is essential to understand that time dilation and length contraction are not two separate, independent phenomena. They are intimately connected, two sides of the very same coin. Both arise as direct consequences of the single foundational principle of special relativity, the constancy of the speed of light. They are the mathematical and physical adjustments that space-time must make to ensure that this one universal law is never broken, no matter your frame of reference. One cannot exist without the other. They are the twin pillars that support the entire structure of relativistic physics and our modern understanding of motion. They are the language space-time uses to describe motion. These concepts fundamentally reshape our understanding of what high-speed travel entails. They offer a glimpse into a universe that is far stranger and more flexible than our everyday intuition suggests. For a traveler on a near light-speed journey, the experience would be profoundly different from what an observer back home witnesses. The traveler could cross vast interstellar distances within their own lifetime because their clock runs slow and the distance they perceive shrinks. This offers a tantalizing, albeit one-way ticket to the stars. A journey to a star 100 light-years away might only take a few years from the astronaut's perspective, making it a feasible mission for an individual. However, this relativistic solution comes with a heavy price. While the astronaut arrives at their destination having aged only a few years, more than a century would have passed on Earth. They would return to a world where everyone they knew is gone, where society has moved on without them. This is the tragic heart of the twin paradox. It means that while high-speed travel makes exploration possible for the explorer, it makes it impossible to maintain a connection with the civilization left behind. It solves the problem of travel time for the individual, but it creates an insurmountable barrier of time for society, reinforcing the notion that faster-than-light travel is needed for true interstellar community. Ultimately, time dilation and length contraction define the rules of the game for any travel near the cosmic speed limit. They are not obstacles to be overcome by better engineering in the traditional sense, but fundamental properties of the universe we must work with. They show us that while we can bend the experience of time and space through speed, we cannot break the underlying speed limit. This forces us to think more creatively, to look for ways to bypass these rules altogether. It is this realization that leads scientists away from simple acceleration and towards more exotic concepts like warp drives and wormholes, ideas that seek not to travel through space but to manipulate the fabric of space-time itself. The most immediate and perhaps most insurmountable barrier to achieving faster-than-light travel through conventional acceleration is the staggering energy requirement. As established by Einstein's special theory of relativity, an object's mass is not a static property but increases with its velocity relative to an observer. This relativistic mass grows slowly at first, but as an object approaches the speed of light, the increase becomes exponential. This is not just a theoretical curiosity, it is a fundamental aspect of how energy and matter interact. Every increment of speed you add requires more energy than the last, creating a wall of ever-increasing resistance that is built into the very fabric of the cosmos. It is the universe's own braking system, preventing massive objects from running wild. This principle has devastating consequences for our interstellar ambitions. To accelerate even a small 1-ton spacecraft to a significant fraction of light speed, say 90%, would demand an amount of energy that dwarfs our current global production. The energy required would be equivalent to many years of the entire world's energy consumption, an astronomical figure that is far beyond our present capabilities, and that is just to get close to the speed limit. The true problem emerges as we try to get even closer. Pushing that same spacecraft from 99% to 99.9% of light speed would require a vastly greater amount of energy than all the previous acceleration combined. A clear demonstration of diminishing returns on a cosmic scale. The ultimate barrier is reached at the speed of light itself. As an object's velocity approaches c, its relativistic mass spirals towards infinity. Consequently, the energy needed to provide that final push to reach the speed of light also becomes infinite. An infinite amount of energy is, by definition, an unattainable quantity. It is more energy than exists in the entire observable universe. This is not a limitation of our technology, like needing a better rocket fuel or a more efficient engine. It is a fundamental law of physics. It means that no matter how advanced our civilization becomes, we can never simply accelerate a ship with mass to the speed of light, let alone beyond it. It is a physical impossibility. Therefore, the dream of simply building a faster engine to break the light barrier is fundamentally flawed. The energy problem closes the door on any brute force approach to faster-than-light travel. It forces us to recognize that if we are ever to reach the stars in a practical time frame, we cannot do it by traveling through space in the conventional sense. The laws of physics as we currently understand them are clear. The front door is locked and barred by the infinite energy requirement. This realization is what compels scientists to search for side entrances, for clever ways to circumvent this law rather than trying to defy it, leading to more exotic and speculative theories of propulsion. Beyond the immense physical barrier of energy, faster-than-light travel presents a profound and deeply troubling logical problem. It threatens to shatter the principle of causality. Causality is the simple, intuitive, and fundamental idea that a cause must always precede its effect. You switch on a light, cause, and then the room illuminates effect. You throw a stone, cause, and then it makes a splash in a pond, effect. This linear, one-way progression of events forms the basis of our understanding of reality, of history, and of the very flow of time. It is the rule that ensures the universe is logical and consistent, preventing the past from being changed by the future and keeping the timeline intact. However, the framework of special relativity shows that if information or an object could travel faster than light, this orderly sequence of cause and effect would break down, because the simultaneity of events is relative, meaning different observers in motion can disagree on the order of events that happen in different places. Faster than light travel would allow for scenarios where an effect could be observed before its cause. From some moving frames of reference, a spaceship arriving at its destination faster than a light signal could be perceived as arriving before it even departed. This would create a universe where the past is not fixed, and history is not a reliable record of what has occurred. This leads to a host of famous and unsettling logical paradoxes. The most well-known is the grandfather paradox. Imagine you could travel back in time, which faster-than-light travel could theoretically enable and prevent your own grandfather from meeting your grandmother. If you succeeded, you would never have been born. But if you were never born, you could not have traveled back in time to interfere in the first place. This creates an impossible, self-negating loop from which logic cannot escape. The universe, as we understand it, simply does not seem to permit such contradictions. The principle of causality appears to be a self-protection mechanism, a fundamental law that preserves the logical integrity of space-time. For this reason, many physicists believe that the universe must have some inherent rule that forbids faster-than-light travel or communication in order to protect causality. This is sometimes referred to as the chronology protection conjecture. It suggests that the laws of physics themselves are conspired in such a way as to prevent time travel paradoxes from ever occurring. While we may find ways to warp space or create wormholes, this principle implies that nature will always find a way to stop us from using them to violate history. The tyranny of causality is therefore a barrier that is just as formidable as the infinite energy requirement, a logical firewall that may be even harder to bypass than any physical obstacle. Even if we could somehow sidestep the colossal energy demands and the paradoxes of causality, the practical, physical realities of traveling at or near the speed of light present a host of deadly engineering challenges. The universe is not perfectly empty. Interstellar space, while a near-perfect vacuum by earthly standards, is still populated with stray atoms of hydrogen, microscopic dust particles, and other bits of cosmic debris. At everyday speeds, these particles are completely harmless, but for a spacecraft traveling at a significant fraction of the speed of light, they become lethal projectiles. The kinetic energy of an impact increases with the square of the velocity, and at relativistic speeds, this effect is amplified tremendously. A collision with a single grain of sand for a ship moving at 99% of the speed of light would release energy equivalent to a powerful explosion, capable of instantly vaporizing the spacecraft. Even impacts with individual hydrogen atoms would become a constant source of intense, high-energy radiation, bombarding the ship and its occupants with a deadly stream of particles. This means any relativistic starship would require a form of shielding far beyond anything we can currently conceive. It would need to be able to withstand constant high-energy impacts and deflect a barrage of radiation that would be fatal to any human crew and destructive to any electronic systems on board. Furthermore, the act of navigation at such incredible speeds would be an unprecedented challenge. At near light velocity, the view from the cockpit would be bizarrely distorted. Starlight from ahead would be Doppler shifted into the high-energy X-ray and gamma-ray parts of the spectrum, posing yet another radiation threat. Light from behind would be shifted into low-frequency radio waves. The field of view would contract into a narrow tunnel ahead of the ship, Navigating through a star system, avoiding planets, asteroids, and other hazards, would require computational systems and sensors of unimaginable speed and precision, capable of reacting to new information in fractions of a microsecond to make course corrections. Finally, there is the issue of acceleration and deceleration. Human beings can only withstand a certain amount of g-force. Even accelerating at a constant and comfortable 1g, the feeling of normal gravity on Earth, it would take almost a full year to reach a velocity close to the speed of light. Any attempt to accelerate faster would crush the occupants. Similarly, the ship would need to begin its deceleration phase long before reaching its destination, a process that would also take a significant amount of time and an enormous expenditure of energy. These material and physical realities add another layer of profound difficulty, showing that even if the theoretical barriers were removed, the engineering task would be a monumental undertaking for any civilization. Despite the seemingly absolute barriers imposed by relativity, physicists have dared to imagine ways to circumvent the cosmic speed limit. The most famous of these ideas is the warp drive, a concept brought from science fiction into the realm of theoretical physics by Mexican physicist Miguel Alcubierre in 1994. The Alcubierre drive proposes a truly radical solution. Instead of trying to move a spacecraft through space faster than light, it suggests moving a piece of space itself. The idea is to manipulate space-time in a very specific way, creating a warp bubble around the spacecraft. This bubble would work by contracting space-time in front of the ship and expanding space-time behind it, creating a wave that the ship could ride. The genius of this concept is that the spacecraft inside the bubble would technically be stationary. It would float in its own local patch of flat, undisturbed space-time, much like a surfer on a surfboard. The surfer is not moving through the water, but is being carried along by the wave. In the same way, the spaceship would be carried forward by the moving distortion of space-time. Because the ship itself is not moving faster than light within its local bubble, it does not violate the laws of special relativity. The bubble and its contents could, in theory, travel at any arbitrary speed, effectively achieving faster-than-light travel relative to the universe outside. It is a clever way to cheat the system without breaking its fundamental rules. However, the Alcubierre drive comes with a monumental catch. To create the required distortion in space-time, the contraction and expansion, the theory demands the existence of something called exotic matter. This is not just a new type of material we have yet to discover. It is a hypothetical substance with physical properties that seem to contradict the known laws of physics. Specifically, it would need to have a negative energy density, or negative mass. This would give it a kind of anti-gravitational effect, pushing space apart rather than pulling it together. As of today, no such matter has ever been observed, and we have no idea how we could possibly create or contain it in the vast quantities needed. The energy requirements for such a drive are also a major hurdle. Early calculations suggested that creating a stable warp bubble large enough for a small spacecraft would require an amount of negative energy equivalent to the mass of the planet Jupiter, while more recent theoretical refinements have suggested ways to drastically reduce this requirement. The amount of energy, whether positive or negative, remains far beyond anything we can currently produce. The Alcubierre drive, therefore, remains a beautiful and elegant theoretical solution, a mathematical possibility that shows us a potential path forward, but one that is blocked by our current understanding of physics and our technological limitations. It is a signpost pointing towards a destination we do not yet know how to reach. Another captivating theoretical proposal for bypassing the vast distances of interstellar space is the concept of a wormhole. Officially known as an Einstein-Rosen bridge, a wormhole is a hypothetical topological feature of space-time that could act as a shortcut through the cosmos. Imagine space-time is a large sheet of paper. To get from one point to another, you would normally travel across its surface, but if you could fold the paper over and punch a hole through both layers, you create a tunnel connecting two distant points directly. A wormhole proposes to do the same thing with the four-dimensional fabric of space-time itself, connecting two vastly separated regions of the universe. This idea emerges from Einstein's general theory of relativity, which describes how mass and energy curve space-time to create gravity. Under certain conditions, these equations permit solutions that look like tunnels through the cosmic fabric. If a wormhole were traversable, a spacecraft could enter one mouth in our part of the galaxy and emerge almost instantaneously from the other mouth in a different galaxy, millions of light years away. The journey through the wormhole itself might be very short, even though the path through normal space is immense. This would not be faster than light travel, but a way of making the journey shorter, achieving the same result. As with the warp drive, this possibility comes with enormous theoretical problems. The first issue is stability. According to general relativity, most wormholes would be incredibly unstable. They would collapse in on themselves the instant anything tried to pass through them. To keep a wormhole open, you would need exotic matter with negative energy density. This same impossible substance required for the Alcubierre drive appears to be a prerequisite for holding a cosmic shortcut open. Furthermore, even if we could find exotic matter and build a stable wormhole, we would have no way of creating one or placing it where we want it to go. Some theories speculate that microscopic wormholes might pop in and out of existence in the quantum foam of space-time, but we would need to find one, enlarge it to macroscopic size, and move one of its mouths to our desired destination. This would require technological mastery over the structure of space-time that is currently pure fantasy. Wormholes remain a fascinating theoretical possibility, a reminder that our universe may contain hidden pathways, but they are not a practical solution for faster-than-light travel with our current scientific knowledge. The strange and non-intuitive world of quantum mechanics has also provided fertile ground for speculating about faster-than-light phenomena. One such effect is quantum tunneling. This is a real observed phenomenon where a particle, like an electron, can pass through a potential barrier that it classically should not have enough energy to overcome. It's as if the particle tunnels through the wall instead of climbing over it. In some experiments, the time it takes for a particle to tunnel through a barrier appears to be so short that its effective speed is calculated to be faster than light. This has led to exciting headlines and speculation about faster-than-light communication. However, this is not the breakthrough it might seem. While the peak of the particle's wave packet can indeed appear on the other side of the barrier faster than a light beam would, this does not allow for the transmission of useful information faster than light. The shape of the wave packet is altered during tunneling in such a way that no actual signal, no cause and effect message can be sent from one side to the other in a way that violates causality. The universe, it seems, has clever ways of closing these potential loopholes. So, while quantum tunneling is a fascinating glimpse into the weirdness of the subatomic world, it does not offer a viable method for building a faster-than-light telephone or starship. Another more speculative idea from the realm of theoretical physics is the existence of tachyons. Tachyons are hypothetical particles that are defined by the property that they always travel faster than light. In the mathematics of relativity, they would have what is known as an imaginary rest mass. Unlike normal matter, which must always travel slower than light, and massless particles, which must always travel at the speed of light, tachyons would be born in the faster-than-light realm and could never slow down to the speed of light. To do so would require an infinite amount of energy, just as it takes infinite energy for us to reach light speed. The existence of tachyons is highly problematic for physics. If they existed and could be used to send signals, they would lead to the same causality paradoxes we have already discussed, allowing messages to be sent into the past. To date, there is absolutely no experimental evidence to suggest that tachyons are real. They remain a mathematical curiosity, a what-if scenario that physicists explore to test the boundaries of their theories. While they are a staple of science fiction, in the world of science fact, they are little more than a ghost in the equations, a particle that the universe does not seem to permit in order to protect its own logical consistency. The significant barrier of requiring negative energy exotic matter has long made concepts like the Alcubierre drive seem like pure fantasy. However, recent theoretical work has begun to challenge this assumption, opening up exciting new avenues of research. In 2021, physicist Dr. Eric Lentz proposed a new class of solutions within general relativity that could, in principle, allow for faster-than-light travel without any need for negative energy. His model describes a new type of warp bubble made from hyperfast solitons, which are stable, compact waves that can travel at any speed and maintain their shape. These solitons are constructed from purely positive energy densities, meaning they could theoretically be created from normal matter and energy. This development is a significant theoretical breakthrough. It suggests that the fundamental barrier to faster-than-light travel might not be an absolute law of nature, but rather a gap in our understanding. Lentz's work, along with similar independent research by other physicists, has shown that there are mathematical pathways to faster-than-light travel that are consistent with the known laws of physics and do not rely on impossible ingredients. This shifts the problem away from needing to discover new exotic physics and moves it into the realm of an extreme but potentially solvable engineering challenge. It provides a more concrete and physically plausible foundation for the future study of warp drives. Of course, this does not mean that building a warp drive is now easy. The energy requirements for these new positive energy models are still astronomical. The initial calculations for Lentz's soliton drive suggest it would need an amount of energy equivalent to the mass of hundreds of suns, compressed into a space smaller than a spacecraft. This is many orders of magnitude beyond anything humanity could ever hope to harness. The primary focus of current research, therefore, is to find new mathematical configurations or physical principles that could drastically reduce these immense energy demands down to a more manageable, albeit still huge, level. It's a long road, but the first step has been taken. These new theories represent a major shift in the scientific conversation around faster-than-light travel. They have moved the topic from the fringes of speculative thought towards a more mainstream area of active research. Scientists are now developing computational tools like the Warp Factory Simulation Suite to test these new ideas numerically and explore different warp field designs. While the journey to building a functional faster-than-light starship remains incredibly long and uncertain, these recent advances have provided a renewed sense of optimism. They suggest that the dream of reaching the stars may not be impossible after all, but merely waiting for the next great breakthrough in our understanding of the cosmos. Even if theoretical physicists provide a perfect blueprint for a faster-than-light drive, the task of building it falls to engineers who must confront challenges of an almost unimaginable scale. The first and most profound of these is energy. Whether it is the negative energy of the Alcubierre drive or the positive energy of newer soliton models, the quantities required are, well, astronomical. The latest theories, while avoiding exotic matter, still call for energy equivalent to the mass of entire stars or planets. This is not something that can be supplied by a conventional power source. It would require a technology capable of converting mass directly into energy with near-perfect efficiency, something akin to harnessing the power of a miniature sun. This leads to the monumental challenge of energy generation. A starship would need its own power plant capable of generating and releasing energy on a scale that frankly dwarfs our entire global civilization's output. Technologies like matter-antimatter annihilation, while theoretically the most efficient energy source possible, are themselves fraught with danger and difficulty. We can currently produce antimatter only in minuscule amounts at a colossal energy cost. To create the kilograms or tons needed for a single warp journey would require a manufacturing capability far beyond our wildest dreams. The ship would essentially need to carry its own Big Bang in a box, a source of power that is as dangerous as it is potent. Once this incredible amount of energy is generated, it must be contained and controlled with absolute precision. Any failure in the containment system would be instantly catastrophic, not just for the ship, but for its entire surroundings. A containment breach would release an explosion that could potentially rival a supernova, obliterating the ship and anything nearby. Engineers would need to design magnetic fields of impossible strength and stability, or perhaps manipulate the fabric of space-time itself just to hold the power source in check. The materials used to build the reactor and its containment vessel would need to withstand temperatures, pressures, and energy fluxes that no known substance could possibly endure. We would have to invent entirely new states of matter to even begin construction. Therefore, the engineering of an FTL drive is fundamentally a problem of mastering energy at a cosmic level. It is not just about building a bigger engine, it is about learning how to safely handle the creative and destructive forces of the universe itself. The ship's power core would be less like a machine and more like a controlled star, a tamed singularity. The practical challenges of generating and storing and precisely manipulating such vast energies are perhaps even more daunting than the theoretical physics that underpins the drive. Before we can warp space-time, we must first prove ourselves capable of safely holding the power of a star in our hands. Beyond the central challenge of the FTL drive itself, the very structure of the Starship would need to be engineered to a standard that is currently unthinkable. Traveling at relativistic speeds, even within the supposed safety of a warp bubble, exposes a vessel to extreme environmental hazards. The boundary of the warp bubble, where space-time is being violently distorted, would likely be a region of intense energy and exotic particles. Any material instability or structural weakness in the hull could lead to the bubble's collapse or a catastrophic interaction with the highly energetic fields. The ship's structural integrity would need to be absolute, capable of withstanding forces that would tear any conventional vessel apart at the atomic level. The problem of shielding becomes paramount. While the warp bubble might protect the ship from interstellar dust, it might also generate its own lethal radiation. Early models of the Alcubierre drive suggested that the front of the bubble would accumulate interstellar particles, potentially releasing them as a devastating blast of gamma rays upon arrival at the destination. The crew and the ship's delicate systems would need to be protected from this and other unknown radiation hazards. This would require shields made not of simple metal alloys, but perhaps of active energy fields or layers of exotic materials specifically designed to absorb or deflect energies that would be fatal to any form of life. Furthermore, the materials used to construct the ship would need to be almost magical by today's standards. They would need to be incredibly strong yet lightweight, capable of enduring extreme gravitational tidal forces and perhaps even able to repair themselves on the fly. At such speeds and energies, even minor structural fatigue could cascade into a total systems failure. Engineers might need to turn to concepts like programmable matter or materials whose properties can be actively managed and reinforced by onboard computer systems. The ship would not be a static object, but a dynamic system, constantly adjusting its own physical structure to survive the hostile environment of warped space-time. The internal environment of the ship also presents significant challenges. The crew must be protected from the gravitational effects of the drive. While the interior of the warp bubble is supposed to be a calm, zero-G environment, any imperfection or fluctuation in the warp field could create violent tidal forces, that would crush the occupants. Life support systems would need to be completely closed-loop, capable of recycling air, water, and food for journeys that, while short for the crew, could still last for months or years. Building a ship for FTL travel is about creating a perfect, unbreakable, self-sustaining bubble of life, a tiny island of stability in a sea of unimaginable cosmic violence. Assuming engineers could build a ship with a working FTL drive, the next immense challenge would be to navigate it. Traveling faster than light means that you are by definition outrunning the very information you need to see where you are going. Light from distant stars and obstacles would not reach the ship in time for it to react. Conventional telescopes and sensors would be useless. The view from the cockpit would not be a starry vista, but a distorted, dangerous mess of blue-shifted radiation ahead and red-shifted waves behind. Navigating this blind landscape would require a completely new form of sensory technology, one that does not rely on light or any other known particle. Perhaps the ship would need to use some form of quantum sensor that could detect the gravitational signatures of stars and planets from a great distance, almost instantaneously. It might need to navigate by creating and reading tiny ripples in the fabric of space-time itself, allowing it to feel its way through the cosmos rather than seeing it. The ship's main computer would need to process this information with incredible speed, building a three-dimensional map of the surrounding space in real time and making trillions of calculations per second to plot a safe course. A single miscalculation, a failure to detect a rogue planet or a dense dust cloud, could be fatal. The precision required for FTL navigation is mind-boggling. Arriving at a destination is not as simple as pointing the ship at a star and engaging the drive. A tiny error in the initial trajectory calculation would be magnified over the vast interstellar distance, causing the ship to miss its target system by millions of kilometers. The ship would need to know its exact position and velocity in space-time with an accuracy that is far beyond our current capabilities. Our global positioning system is accurate to within a few meters. An FTL navigation system would need to be accurate to within centimeters or less, all while traveling at many times the speed of light across light years of empty space. Finally, there is the problem of controlling the warp bubble itself. How do you steer it? How do you slow down and stop? Disengaging a warp drive would likely be as complex and dangerous as starting it up. The process would need to be perfectly controlled to avoid releasing a catastrophic burst of energy or creating a destructive gravitational wave. The ship's navigation and propulsion systems would have to be flawlessly integrated, allowing the pilot or computer to make minute adjustments to the shape and intensity of the warp field to steer the vessel. Navigating through warped space-time is not like sailing the seas. It is like trying to rewrite the laws of physics on the fly, a task requiring a level of control that remains pure science fiction. Science fiction has long been the primary domain of faster-than-light travel, serving as a vast and imaginative playground where the constraints of physics can be conveniently set aside. For decades, authors and filmmakers have used concepts like warp drives, hyperspace, and jump gates not just as technological marvels, but as essential narrative tools. These inventions are the engines of interstellar storytelling, allowing characters to hop between star systems, engage in galactic politics, and encounter diverse alien civilizations. Without FTL, the sprawling space operas that have captivated generations would be impossible, their stories bogged down by the millennia-long journeys that real physics would demand. This creative freedom allows science fiction to explore the what-if scenarios that science itself cannot yet touch. In Star Trek, the warp drive is more than just a propulsion system. It is a symbol of an optimistic, united human future. It represents a mastery of physics that has enabled a post-scarcity society to reach for the stars. In Star Wars, hyperspace is a mystical, almost chaotic dimension, navigated by daring pilots and advanced computers, that adds adventure and peril to every journey. These fictional depictions, while scientifically inaccurate, have had a profound influence on both the public and the scientific community, planting the seeds of ambition for what might one day be possible. The relationship between science fiction and science fact is not a one-way street. These wildly imaginative stories have directly inspired real-world scientists to investigate the very possibilities they depict. The term warp drive itself was famously popularized by Star Trek long before Miguel Alcubierre formulated his mathematical model. It is no coincidence that his theory, which involves warping space-time, bears a striking resemblance to the fictional technology. This creates a fascinating feedback loop. Fiction presents a compelling dream, and science begins the slow, methodical work of figuring out if it could ever be made real. Many physicists and aerospace engineers today credit their early love of science fiction as the spark that ignited their careers. This inspirational role is perhaps science fiction's greatest contribution to the FTL quest. It acts as a cultural and intellectual catalyst, constantly pushing the boundaries of what we dare to imagine. By presenting us with visions of a future where humanity is an interstellar species, it gives scientists a grand goal to strive for and provides the public with a framework for understanding why such research matters. While the fictional technologies often gloss over the immense challenges, they succeed in their most important task: keeping the dream of the stars alive in our collective consciousness, ensuring that we continue to ask the big questions and reach for the seemingly impossible. While science fiction provides the inspiration, it must, by its very nature, take significant liberties with scientific reality. The primary goal of a story is to engage an audience, and the complex, often paradoxical nature of real FTL theory can be a narrative roadblock. For instance, the Alcubierre drive, even in its most theoretical form, comes with a host of inconvenient side effects that are rarely shown on screen. These include the inability to communicate with the outside universe while in the warp bubble, the potential for a catastrophic release of energy upon arrival, and the fact that the ship cannot actually be steered from within the bubble in any conventional sense. For the sake of a clean and exciting story, these details are almost always ignored. Another major area of divergence is the depiction of energy. In films and television shows, engaging a warp or hyperdrive is often as simple as flipping a switch or pulling a lever. The colossal energy requirements, equivalent to the mass of planets or stars, are hand-waved away with techno-babble about dilithium crystals or hypermatter cores. This is a necessary fiction, as a realistic portrayal of the energy generation and containment needed would completely dominate the story, turning an adventure into a complex engineering documentary. Science fiction prioritizes the journey and the destination, not the mind-boggling power plant required to make it happen, which is a perfectly reasonable choice for entertainment. Similarly, the concept of hyperspace, as seen in franchises like Star Wars or The Foundation, is a pure plot device with no basis in current physics. It posits the existence of a separate dimension where the laws of physics are different, allowing for incredible speeds. This neatly sidesteps all the problems of relativity, time dilation, and causality within our own universe. It provides a convenient and visually spectacular way to represent FTL travel, a swirling tunnel of light, without getting bogged down in the messy details of general relativity. While a useful narrative shortcut, it deliberately moves the concept from the realm of science into the realm of fantasy, trading scientific plausibility for storytelling efficiency. Ultimately, the gap between FTL in science fiction and science fact is a necessary and healthy one. Science fiction's role is to inspire, to wonder, and to entertain, while science's role is to investigate, to calculate, and to test. The simplified and dramatized versions of FTL travel we see in stories are not failures of imagination, but successful acts of communication. They translate a deeply complex and abstract scientific concept into something an audience can understand and get excited about. As real science slowly and painstakingly explores the genuine possibilities, it will always be guided, in part, by the fantastic and impossible dreams that science fiction first dared to show us. For many decades, the scientific discussion around faster-than-light travel was largely confined to the fringes of theoretical physics. The immense barriers of infinite energy and causality paradoxes made it seem like a dead end, a fascinating but ultimately impossible dream. However, in recent years, this perception has begun to change in a significant way. A series of theoretical breakthroughs and a renewed sense of scientific curiosity have started to shift the conversation. FTL travel is slowly moving from the realm of pure speculation towards something that, while still incredibly distant, could be considered a plausible long-term engineering goal. This new optimism is not based on wishful thinking, but on solid mathematical and theoretical work. The most significant change has been the move away from ideas that require impossible ingredients. For a long time, concepts like the Alcubierre drive and traversable wormholes were fundamentally dependent on the existence of exotic matter with negative energy density. As no such substance has ever been found, these ideas remain tantalizing but impractical. The recent development of new theoretical models that can achieve the same space-time warping effects using only positive energy, the kind of energy and matter that we know exists, has been a complete game-changer. This has removed what was once considered the single greatest theoretical obstacle, opening the door for more serious and grounded scientific investigation into the mechanics of warp drives. This shift has been supported by the development of powerful new computational tools. Scientists can now create sophisticated computer simulations to model the behavior of space-time under the influence of extreme energy densities. Tools like the open-source Warp Factory suite allow researchers to design and test different warp field configurations virtually, exploring their stability, energy requirements, and potential side effects without needing a physical experiment. This accelerates the pace of research dramatically. It allows the scientific community to collaboratively refine theories, identify promising avenues, and rule out unworkable ideas much more efficiently than ever before. It is a crucial step in turning abstract mathematics into something that could one day be engineered. As a result of these developments, the topic of FTL travel is gaining a new level of legitimacy within the scientific community. Mainstream research institutions and even space agencies like NASA are now openly discussing and funding preliminary research into these advanced propulsion concepts. The establishment of dedicated research groups and funds, such as the Advanced Propulsion Laboratories Warp Fund, signals a growing recognition that this is a field worthy of serious study. While no one is promising a Starship next Tuesday, the scientific consensus is evolving. The question is no longer a simple "is it possible?" but has become a more nuanced and hopeful "what will it take to make it possible?" At the heart of this renewed optimism are the new theories themselves, which offer a more physically plausible path to faster-than-light travel. The work of physicists like Dr. Eric Lentz and other independent research groups has introduced the concept of solitons as a basis for warp drives. A soliton is, well, a self-reinforcing solitary wave that maintains its shape while it travels at a constant speed. The new theories propose creating a stable soliton of curved space-time that encloses a flat, undisturbed region where a spacecraft could sit. This wave of space-time would be generated using only positive energy and regular matter, albeit arranged in incredibly complex and dense configurations, completely circumventing the need for exotic matter. These new solutions are not just minor tweaks to old ideas. They represent a fundamentally different approach. They are derived directly from Einstein's equations of general relativity, proving that faster-than-light solutions are permitted within the existing framework of physics without needing to invent new laws. This is a crucial point. It suggests that the ability to warp space-time might be a natural, if extreme, consequence of the universe's own rules. The challenge then becomes one of technology and energy, not one of rewriting our entire understanding of physics. It grounds the faster-than-light dream in the science we already know, making the path forward clearer even if it is extraordinarily difficult. However, the primary obstacle for this new generation of warp theory remains the colossal energy requirement. The initial models for these positive energy drives demand an amount of energy equivalent to the mass of hundreds of Jupiters or even entire stars. These are numbers so vast that they are almost meaningless in any practical sense. The main focus of current theoretical research is therefore to find ways to drastically reduce this energy cost. Scientists are exploring different shapes and compositions for the soliton, looking for more efficient configurations that could lower the energy needed by many orders of magnitude. The goal is to bring the requirement down to a level that, while still enormous, might one day be achievable by a highly advanced civilization. This research has also begun to address some of the other practical problems associated with warp drives. Scientists are simulating what happens at the boundary of the warp bubble, how it might interact with interstellar matter, and how a pilot might control such a craft. For example, some models suggest that these new warp bubbles could be switched on and switched off without the catastrophic energy releases predicted by older theories. While these are still early days, every theoretical refinement brings us one small step closer to a complete and workable blueprint. The new generation of warp theory is methodically building the scientific foundations upon which a future technology could one day stand. Looking ahead, the road to developing any kind of functional, faster-than-light prototype is exceptionally long and filled with monumental challenges. The journey will likely unfold over many decades or even centuries and will depend on breakthroughs in multiple fields of science and engineering. The immediate next step for researchers is to continue refining the theoretical models. The primary goal is to drastically reduce the energy requirements. If a new mathematical insight could lower the needed energy by 30 or even 60 orders of magnitude, as some researchers hope is possible, then the concept would move from the realm of the purely theoretical into the world of the potentially practical. This is the first great hurdle that must be overcome. The next stage would be to devise some form of experimental test, even on a microscopic scale. We are a very long way from building a full-size warp drive, but it might be possible to create a tiny, fleeting distortion in space-time in a laboratory setting. This could involve using incredibly powerful lasers or intense electromagnetic fields to concentrate a huge amount of energy into a very small space. The goal would be to observe the predicted space-time warping effects, even for a fraction of a second. Such an experiment, if successful, would be a landmark achievement in physics. It would provide the first concrete proof that our theories are correct and that manipulating space-time is physically possible. If these microscopic tests prove successful and the energy requirements become manageable, the focus would then shift to engineering on an entirely new scale. Humanity would need to develop revolutionary new energy sources far beyond nuclear fission or fusion. We would need to master material science to create structures that can withstand the immense forces involved. And we would need to develop advanced artificial intelligence and control systems capable of navigating and managing a warp field with perfect precision. This phase of development would represent an engineering project greater than any in human history, requiring global cooperation and resources on an unprecedented level. It is a multi-generational effort. So while recent developments have injected a thrilling new dose of hope into the quest for faster-than-light travel, we must remain realistic. The road ahead is not a sprint but a marathon. The challenges remain as immense as the potential rewards, yet, for the first time, that road is visible. We can see the steps, refine the theory, reduce the energy, conduct small-scale experiments, and then perhaps begin the grand project of building a prototype. The dream of reaching the stars is still a distant one, but thanks to the tireless work of scientists today, it is no longer just a dream. It is a destination on the far horizon of human endeavor. The achievement of faster-than-light travel would represent far more than a mere technological victory. It would trigger a philosophical earthquake, shaking the very foundations of our understanding of reality. Central to our perception of the universe is the linear flow of time and the unwavering principle of causality, where cause always precedes effect. But as physics suggests, faster-than-light travel could shatter this simple, comforting linearity. The ability to outrun a beam of light could, from certain frames of reference, make it possible for an event to be observed before its cause has even occurred. This is not just a scientific curiosity, it is a direct challenge to the logical structure of existence, forcing us to confront a universe that may not be as orderly as we believe it to be. This potential violation of causality would compel a radical re-evaluation of concepts like free will and determinism. If the future can influence the past, does this imply that all of time, past, present, and future, already exists in a single static block? This block universe theory, long a topic of philosophical debate, would suddenly become a tangible reality we might have to navigate. In such a universe, our perception of making choices and shaping the future could be an illusion, a trick of our limited, linear consciousness. We would be forced to grapple with the unsettling possibility that we are merely actors, reading from a pre-written script, with faster-than-light travel being the technology that allows us to peek at the pages ahead or behind. Furthermore, our very sense of self and identity is deeply rooted in the continuous, uninterrupted flow of our memories and experiences through time. What would happen to human consciousness if it could be transmitted across the stars faster than light? If a person's mind could be uploaded and sent to a distant world, arriving before they even left, which version is the real one? This would ignite profound debates in neuroscience and philosophy about what constitutes personal identity. Is consciousness merely information that can be copied, or is it tied to a specific physical form? Faster-than-light travel would blur the lines between the original and the copy, the self and the other, potentially dissolving our traditional notions of individuality and the soul. Ultimately, the philosophical implications would force humanity to mature into a species that can comprehend a far more complex and less intuitive cosmos. Our epistemology, the very way we acquire and validate knowledge, would have to adapt. Scientific observation would no longer be a passive act of receiving ancient light from distant stars, but could become an active, real-time engagement with the galaxy. This would change our relationship with the universe from one of a distant observer to that of an immediate participant, with all the profound responsibility that entails. Faster-than-light travel would not just let us visit the stars, it would fundamentally change how we think about them, about ourselves, and about the nature of reality itself. The advent of faster-than-light travel would, irrevocably alter the course of human civilization, likely leading not to a unified galactic empire, but to a great and rapid fragmentation of our species. With the ability to cross interstellar distances in weeks or months, colonies could be established on countless worlds across the galaxy. Initially connected by this new technology, these settlements would soon begin to diverge. Each world, with its unique gravity, atmosphere, and ecosystem, would impose different evolutionary pressures. Over generations, isolated human populations would adapt to these new environments, potentially leading to the emergence of distinct subspecies of humanity, physically and culturally unrecognizable to one another. This diversification would extend deep into our social and political structures. Centralized governance from Earth or any single core world would become honestly both impractical and undesirable. The vast distances, even when traversable, would foster a spirit of independence and local autonomy. New political systems, ideologies, and forms of society would blossom in isolation, each tailored to the specific conditions and philosophies of its home world. We might see the rise of confederations, decentralized networks, or perhaps political structures so alien we cannot yet conceive of them. The single story of humanity would splinter into 1,000 different narratives, and each unfolding on a different world under a different star. The economic landscape would be similarly transformed, potentially ending the concept of scarcity as we know it. With access to the resources of an entire galaxy, materials that are rare and valuable on Earth could become commonplace. This could usher in an era of post-scarcity abundance for some, but it could also create new and more profound forms of inequality. A stark divide could emerge between the FTL-capable spacefaring civilizations and those planets or populations left behind. Access to FTL technology itself could become the ultimate measure of wealth and power, creating new dependencies and potential for exploitation on a galactic scale, with frontier worlds at the mercy of the core systems that control the star lanes. This fragmentation would also reshape human culture. Languages would evolve in isolation, art forms would reflect alien landscapes, and religions would adapt to new cosmic perspectives. While FTL travel would allow for the exchange of ideas, the sheer diversity of experience would ensure that no single culture could remain dominant. Humanity would become a vast and complex tapestry of different civilizations, each contributing its own unique thread. The great challenge would be to maintain a sense of shared identity, to remember the common origin on a small blue planet, even as our species scatters and transforms into something new and wonderfully diverse across the galaxy. Faster-than-light travel would thrust humanity into a new role as a galactic power, and with that power would come an immense and, frankly, unprecedented ethical responsibility. No longer confined to our own solar system, our actions would have consequences on a planetary and perhaps even galactic scale. The first and most pressing ethical question would concern the colonization and terraforming of other worlds. Do we have the right to alter the environment of an entire planet to suit our own needs, especially if that planet already harbors its own form of life, even if it is only microbial? This would force us to develop a new planetary ethic, the framework for deciding when and how it is acceptable to reshape a world. This ethical framework would become infinitely more complex if we were to encounter extraterrestrial intelligence. The history of contact between different human cultures on Earth is, unfortunately, fraught with conflict, misunderstanding, and exploitation. Contact with a truly alien species would present these challenges on an unimaginable scale. We would need to establish new protocols for communication, new principles of interstellar law, and a new ethical code governing our interactions. The prime directive of science fiction, the principle of non-interference with less developed cultures, would become a very real and critical topic of debate. A single misstep could lead to a misunderstanding of cosmic proportions, or worse, an interstellar conflict. The very capability of FTL travel would present its own set of moral dilemmas. The Alcubierre drive, for example, is theorized to potentially release a devastating blast of radiation upon arrival, inadvertently sterilizing the destination. Who is responsible if a ship accidentally destroys an ecosystem or a fledgling civilization? How do we regulate a technology that could, in the wrong hands, be weaponized to deliver destruction at speeds that leave no time for defense? The development of FTL travel would necessitate the creation of interstellar treaties and regulatory bodies to ensure its safe and peaceful use, a task that would make our current geopolitical challenges seem trivial by comparison. Ultimately, the quest for the stars would force us to look inward and define what is best about our own species. It would demand a level of wisdom, foresight, and self-control that humanity has only shown in fleeting moments throughout its history. We would have to become stewards not just of our own planet, but of any part of the galaxy we touch. The development of a robust cosmic ethics would be just as important as the development of the technology itself. Without it, our expansion into the universe could become a story not of glorious exploration, but of cosmic tragedy, spreading our flaws and conflicts to the stars. The quest to travel faster than light represents, really, one of the grandest and most enduring ambitions of the human spirit. It is a dream woven from our innate curiosity, our desire to explore the unknown, and our refusal to accept limitations. For generations, this dream was confined to the pages of science fiction, a fantasy for storytellers. Yet, as we've seen, the line between fiction and scientific inquiry is becoming increasingly blurred. The journey from imaginative concept to theoretical possibility is well underway. The profound barriers of relativity, energy, and causality, which once seemed to render the FTL dream impossible, are now being met with ingenious and scientifically rigorous new ideas that seek to circumvent rather than break the fundamental laws of our universe. The science of FTL travel is no longer a matter of pure speculation. Theoretical physicists are actively developing models such as positive energy warp bubbles and hyperfast solitons that are mathematically consistent with Einstein's general relativity. These concepts, while still far beyond our current technological grasp, provide a plausible scientific foundation for what was once thought to be impossible. They have shifted the nature of the problem. The question is no longer whether the laws of physics permit FTL travel, but rather whether we can ever develop the engineering and energy harnessing capabilities to turn these elegant mathematical solutions into a physical reality. This is a monumental but crucially different kind of challenge. The obstacles that remain are, without question, immense. The energy required for even the most efficient theoretical drive is astronomical, demanding breakthroughs in physics and engineering that could be centuries away. The practical challenges of building a stable craft, navigating blindly at superluminal speeds, and ensuring the safety of any potential crew are equally daunting. Furthermore, the philosophical implications of success, the potential disruption of causality, the redefinition of human identity, and the ethical responsibilities of becoming a galactic species are profound and complex. The path to the stars is not a simple one. It is fraught with challenges that will test the limits of our science, our engineering, and our wisdom. Yet despite these colossal hurdles, there is a tangible and growing sense of optimism in the field. The pace of theoretical discovery is accelerating, driven by new computational tools and a new generation of scientists who are unafraid to tackle these big questions. The journey to achieve faster-than-light travel will be a long one, a multi-generational marathon of discovery and innovation. But for the first time in human history, the destination no longer seems like an impossible dream. It is a distant but visible horizon, a future possibility that we can now begin to chart a course towards, one scientific breakthrough at a time. The quest continues, fueled by the same hope that first made us look up at the stars and wonder. In conclusion, the pursuit of faster-than-light travel is far more than a simple engineering project. It is a reflection of humanity's deepest character. It embodies our relentless drive to explore, to understand, and to push beyond the boundaries of our known world. The science shows us that while the cosmic speed limit is a formidable rule, the very fabric of space-time may be more malleable than we once thought. The theories of warp drives and other exotic propulsion methods suggest that there may be clever ways to navigate the cosmos that are permitted by the laws of physics, offering a glimmer of hope that the vast distances between stars might one day become traversable within a human lifetime. The future of this field will depend on continued dedication to fundamental research. The key lies in reducing the almost unimaginable energy requirements that current theories demand. This will require new insights into the relationship between matter, energy, and the geometry of space-time. It will also demand a willingness to explore the frontiers of science, to invest in long-term, high-risk research that may not yield practical results for decades or even centuries. The road ahead is not a clear, straight path, but a winding journey into the deepest and most challenging questions in all of physics, a journey that will undoubtedly lead to unexpected discoveries along the way. If humanity is to one day succeed in this grand endeavor, the implications will be transformative. FTL travel would not just open up the galaxy to exploration and settlement, it would fundamentally reshape our species, our society, and our philosophy. It would force us to confront our place in the universe with a new sense of maturity and responsibility. The challenges are immense, but the potential reward is the greatest adventure in human history. The chance to become a truly interstellar species, to carry the spark of consciousness from our small blue world out into the vast, silent darkness of the cosmos. Therefore, the dream of traveling faster than light should not be dismissed as mere fantasy. It is a powerful and worthy goal that inspires us to be better scientists, more creative engineers, and more thoughtful philosophers. It is a testament to our ability to look at a seemingly insurmountable barrier and ask, is there another way? While the starships of our science fiction dreams may still be many generations away, the journey to create them has already begun. It is a journey of intellect, imagination, and unyielding hope, a journey that will ultimately define humanity's future in the universe.